Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. A couple of weeks ago, I spent some time at the Strata Data conference in New York City, presented by O'Reilly and Cloudera. And over the course of the next few shows, we'll be bringing you my interviews with some of the awesome speakers that I had the pleasure to meet with. In this episode of our Strata Data series, we're joined by James Dreiss, Senior Data Scientist at international news syndicate Reuters. James and I sat down to discuss his talk at the conference, Document Vectors in the Wild, Building a Content Recommendation System, in which he details how Reuters implemented document vectors to recommend content to users of their new infinite scroll page layout. In our conversation, we take a look at what document vectors are and how they're used, how they tested the accuracy of their models, and the future of embeddings for natural language processing. Before we move on, I'd like to send a quick shout out to our friends at Cloudera and Capital One for their continued support of the podcast and their sponsorship of this series. Cloudera's modern platform for machine learning and analytics, optimized for the cloud, lets you build and deploy AI solutions at scale, efficiently and securely, anywhere you want. In addition, Cloudera Fast Forward Labs' expert guidance helps you realize your AI future faster. To learn more, visit Cloudera's Machine Learning Resource Center at cloudera.com/ml. At the NIPS conference in Montreal this December, Capital One will be hosting a workshop focused on challenges and opportunities for AI in financial services and the impact of fairness, explainability, accuracy, and privacy. A call for papers is open now through October 25th. For more information on submitting, visit twimlai.com/C1NIPS. And now, on to the show. All right, everyone. I am in New York for the Strata conference, and I am here with James Dreiss. James is a senior data scientist at Reuters. James, welcome to This Week in Machine Learning and AI.
Hi, Sam. It's great to be here. Thank you very much.
Awesome. So, James, you've got a background in art history. You've studied economics at graduate school. You currently work at Reuters doing data science. Tell us a little bit about your background.
Yeah, sure. So I think it is sort of a weird background to have art history and English and sort of humanities, but that's what I studied in undergrad, and I sort of kicked around in those worlds for a while in New York City. And eventually I started a nonprofit with a friend that was focused on international development. And that is what led me to grad school. So I studied econometrics and statistics in London. And that was sort of my first exposure to, this sort of world of data science, although at the time it wasn't really talked about as much. And it also first exposed me a little bit to programming. We use something called Strata, which is like a SaaS sort of, statistical software, but you do some coding. So that was a really good sort of skill acquisition period. And after school, I learned R. And there was this great job at the Met Museum in New York that opened up, and they were hiring for predictive analysts. And that was, so given my art history background and also having studied what I studied, this was sort of a perfect combination of those two things. And that was great. I mean, it's, you work at the museum, sort of ruined me for any future office.
It sounds awesome.
Yeah, it was really terrific. I like whatever, I don't really care, if you how many foosball tables you have or how big your LaCroix tower is, because, I can go look at 5 Vermeers at lunch, my lunch break. So that was amazing.
And was your focus there on kind of operational analysis or marketing analysis, or was it art related?
It was more focused on administration and specifically fundraising. So trying to match donors with the museum, people who really love the museum and have the capacity to give. It was interesting because the data there is really, really rich. I work in web analytics now. But there you have postal addresses, and these people really love the museum too. So it's not they're happy to work with you. So that was great. But yeah, a few years ago, I moved to Reuters, and that's where I am now. Yeah, we've done a lot of stuff. We had a big redesign on the website last year, and built out the data science platform. And there's been a lot of stuff in NLP, obviously. And yeah, I'm here giving a talk tomorrow, and that's what I'm focusing on.
Fantastic.
So, yeah.
And for those who don't know Reuters, what does Reuters do, or what is the part of Reuters that you work with do?
Yeah, so Reuters is a news organization. It's international. We do a lot of syndicated news. So we have reporters all over the world, stationed in many different countries. So wherever there's breaking news, a reporter will be there and filing stories. And they go to different outlets, but we also obviously publish ourselves. So, and it's we've been around for well over 150 years, I think.
Awesome.
Yeah.
And so the talk that you're giving tomorrow is called Document Vectors in the Wild, Building a Content Recommendation System. Tell us a little bit about the motivation for this project.
Sure. So last year, we decided to redesign the website and to move to something called an infinite scroll model. A lot of online publishers have moved to this model. Basically, it's one where you click on an article and then you read it, and then you have a string of articles that come after it. So it's a big misnomer because it's of course it's not infinite. In fact, we wanted to just give 5 to 10 articles for the user. And so my job is really to figure out what articles to give to them. And specifically, so we don't have registration on the website, meaning we're not doing too much personalization. About 75% of our users have 2 or fewer articles that they read. So it's really a content-to-content recommendation system.
Okay.
So we did some tests previously and found out that if a user is on a page, if it's a business page or a tech page, they're going to probably want more of that content, which it makes sense. So we started out thinking, we want to find similar content on the site programmatically. And the other challenges were, news is breaking and happens quickly, and editors can't always provide tags, metadata to the articles. So essentially, we need to do categorization just purely based on the text of the article. And maybe some tags as well. So the challenge is really how do you get at specific subtopics within these larger topics that we have, like tech and business, and how do we find articles about discrimination in tech, which is not something that would necessarily be tagged by an editor.
Okay.
Yeah.
And so presumably based on the talk title, you did this using document
Yes.
vectors. We've talked quite a bit about word vectors. What's a document vector?
It's very similar to a word vector. It's sort of like a sidecar to a word vector. In fact, the document vector is treated as another word. So this is like the problem in NLP is that if you just tokenize text and you're just looking at treating the words as these atomic objects, you're losing so much information. If you build a vector that has the word president in it and another one that has the word Trump, those 2 vectors they don't know that Trump is president, which is good for them. But we need to know that sort of thing. Word embeddings, which encode semantic meaning, get at this. But the challenges for us were that we have the length of our articles are highly variable. We have really short articles, really long articles. So doing something like just taking the first 100 words of an article and taking the embeddings for those words wasn't really going to cut it. Having done some research into document vectors, I also knew that performance in these sorts of tasks was higher than just using, word embeddings that were cut off at a certain length or average word embeddings or that sort of thing. So this is something we wanted to explore.
Is that pretty typical for using word embeddings to cut them off at a certain length? Why is there a requirement to do that?
I think, if you wanted to compare 2 articles that were different lengths, you had to, they had to have similar sizes, it's the same sizes. So I'm not sure how wide that is in the industry, but document vectors allow you to obtain vectors that are the same size, where the articles would be different lengths.
And so how do you go about creating these document vectors?
So word vectors, the way I'm sure your audience knows how they are created, but they're very similar. Document vectors happen in a very similar way. So essentially, word vectors are getting at the semantic meaning of words. I usually call them, I treat them as, their addresses basically in this multidimensional space. So you know that the word dog and the word cat are close together because the model on which they were trained determined that their co-occurrence happens frequently. So in the model specifically, it's calculating the probability of co-occurrence, and that's the output layer. And the middle layer is the embedding layer, and that layer is being maximized. So it's sort of set up as this fake prediction task where you're predicting words from context or the opposite. And as a result, you have these weights that are rich with all that semantic information. Now, document vectors are very similar. You're doing the training is virtually the same, but you're just adding an additional vector at the input layer that is representative of the document. So you train in a similar way. You have a context window. You sort of scan across the article, the document, doing the predictions. And at the end, after you've gone through your entire corpus, you have this additional vector that has sort of picked up all of the semantic information that was not picked up by the word vectors. And you can make these comparisons between articles, between documents, because all the documents have shared context and words. So if they have shared context, then the article should be similar.
So you're able to do kind of similar vector operations on these documents. There's the classic word embedding or word vector examples like, man, king, woman, queen kind of thing. You're able to do those similar kinds of things with documents.
Yeah, you're able to compare two articles where they don't share any pieces of text that may not share any words at all and maybe different lengths, and you can know that they have similar meaning, and that's how we got at these subtopics. There are some sort of peculiarities with them, especially with inference. So when you want to make a prediction for a new document that you haven't seen before, you're essentially running an additional training step, or maybe many 10 to 20 training steps, depending on how many epochs you had when you're training the original model. You're also holding the word vectors and the output weights constant. So you hold this constant, you do an additional training step, and this new document vector that was initialized randomly comes to, it essentially picks up all the information that is present in the context and the output layer.
Can you elaborate on that? So
Sure.
This is when you're at inference time, there's a training step?
Yeah, there is. Essentially, so that new vector is initialized randomly. The other weights are held constant. And it's sort of strange. Essentially, you're going to have that new document vector that you're obtaining is going to be a little different each time if you do new inferences. Which is a little strange, but there are ways of getting at to sort of do like sanity checks to know that, okay, this new document vector that I just inferred should be similar to itself, essentially. So one sort of sanity check is you have your model, you've trained it, make inferences on all the training documents that you trained on, and then ensure that those new inferred document vectors their nearest neighbors are themselves. So if that's the case, then your model should be trained correctly.
And so how did you get from these document vectors to the categories?
To the sort of the larger topic categories?
Or to the subcategories?
So,
or both?
Yeah.
Right?
So they're not really, we don't have labels for the subcategories. That just sort of happens. It's a result of having the model. Yeah.
You're clustering in this document space and then manually associating a label with individual clusters.
Yeah. So we put the unsupervised learning model in production, which is I think something unique, and mostly often embeddings are used for downstream tasks as part of the feature of a model, but we're actually using the clusters directly. We got at we tried to ensure that it was accurate, and I can get into that. But one thing that we did, so we're only when we rank the article scrolls, we're ensuring we're first just pulling all tech articles, for instance, and then within tech we rank. Based on the article that the user requested, what are the nearest articles that are within the last 24 hours that are also tech, and there's also like a popularity filter there as well. So
So the example you gave earlier where you were interested in subtopic discrimination in tech, for example, that subtopic is never explicitly identified. It's just it's determined based on the document space.
Right, exactly. I mean, we can go back and look at the labels that were applied by editorial after the fact and get at that sort of thing. But similarly to something like LDA, like it's not, there's not an automatic assignment of label like this is discrimination in tech. You have to sort of, if you're looking at trying to identify subtopics in LDA, you're really just looking at the words that were assigned for that topic. So it's a similar sort of thing.
You were mentioning some of the testing that you were doing around this.
Yeah, it was interesting. So, measuring performance of unsupervised learning models is always a little tricky. There's always some eyeballing that goes on. Like something like doing the elbow method for k-means. Like that's always been sort of hard for me. It's never actually you never get like a true elbow. Like to determine the right number of clusters. There should be like this break in the graph of clusters versus how dispersed they are. But looking through the literature and also remembering other methods, something like silhouette index, which is unsupervised learning metric where you're essentially comparing the average distance of a data point, and between it and its own cluster and its neighboring clusters, and you're trying to get at how close it is between its own cluster and its neighboring ones, and you're assigning accuracy based on that. In one of the doc2vec papers, the authors used something called triplet accuracy, where they took Wikipedia articles and found articles that were in the same topic, and then they took a randomly drawn non-topic article. And if the distance between the two similar topic articles was closer than the non-topic article, then that counted as an accuracy point for the model.
Okay.
So we did something similar. We knew that we wanted to do subtopics. So we for the document vector model, would take two articles in tech and one that was not tech. And if it determined that those two same articles were closer than the one in business or sports or something, then that counted as a point to the accuracy. And we ended up with, I think it was about 77% accuracy, which is very close to what the authors who devised this triplet accuracy found as well.
So you're basing this model on accuracy at the category level, but ultimately you're trying to make inferences at a subcategory level. Did that play into it at all?
In terms of looking at accuracy?
In terms of looking at accuracy or the model, construction or performance?
Yeah, we definitely did some sort of, we couldn't have done too many, but yeah, we looked at, just the performance generally, relied on the editors as well to sort of say like, well, this is a good match. This isn't. But ultimately, the real test of any model is when you put it in production, see the performance. And if it's performing well, if the topic assignment is not good, then, it should perform less well than your control or your other test branch. So that was the ultimate test for us.
And so what was the metric for that test? What are you ultimately trying to drive?
Ultimately we want to drive engagement on our site. There's a lot of ways you can optimize, the way users interact with your website. But engagement is the sort of catch-all thing that if you try to get at that, then you're going to lift all the other ships of, whatever, looking at ads and engaging with the content itself. So that was ultimately what we were trying to get at, and that there are proxies for that. So specifically, how deep a user would get into the article scroll, and also how deep they're getting into the articles themselves. We did 3 different test branches. One where we're having similar scrolls, and one where we have what I was calling dissimilar scrolls. So I had this sort of pet theory that users would get sort of tired of reading the same content. So if you're reading an article about like Trump's cabinet woes, maybe you want to move on to something else after you've read that article. So that was the intuition behind that. So we would, and essentially that's same topic articles, just sorted in reverse cosine order, which essentially what you're obtaining is, there's a lot of randomness there. It sort of doesn't seem, you can't immediately tell that two articles are very dissimilar. It's sort of a strange thing. They're just going to seem like that they were randomly drawn.
Okay.
So that was one test branch. And then as a control, we had top news articles. And yeah, the end result was sort of, what we expected, which is good, which is that similar articles really outperformed. The scrolls outperformed both of these other test branches. And within topic categories as well, things like sports and culture, those performed especially well. Those are sort of on Reuters, they're a little harder to find on our site. So if users are going to those topics, it's likely that, they're going to be highly engaged. So that was the intuition behind that as well. So,
and to what degree did the similar scroll model outperform the other models?
It was a few fractions of percentage, but it's, when you're looking at statistically significant results, that's what you would expect. We were lucky in that, so essentially every article page was a randomized test. So a user comes to the page and they're served one of the three test branches, and that randomization happens at the article level. So we ran hundreds of tests, and that was the real, no matter the lift. I mean, that was very important as well, of course. But in terms of like winning pages, the similar scrolls blew the other two out of the water. So that was a very good signal.
What do you mean by that? Winning pages?
That the one test branch was significant over the other two in terms of these metrics that I mentioned. Okay. So that was counted as a winner. And then if you look at all the pages in aggregate, that was the result.
A couple of random things I remember from flipping through your presentation. There was a reference to Comfifi.
I know. Well, I was trying to. I was like, I really want to use this tweet as an example. Because a lot of people, word embeddings have been around for a while now. I wanted to sort of, liven it up a bit. But yeah, Kofifi, I don't know what would add or subtract, what vectors would add or subtract to equal that. I think it's just it's completely nonsense. So I don't. I want to dig into that a little bit more. And I'm glad that you pronounce it the way I'm going to pronounce it, because I'm not entirely sure. So
I think I pronounce it differently every time I say it, which is not very often.
Well, that's NLP is hard for this reason. I mean, this is like, we're getting at this, like what, pronunciation, meaning, like this is, I mean, someone described English to me the other day, and this is any language, but it's a connotative sort of system. And that really gets at it for me, like in a pithy way, like, it's all built around these connotations. Everything has higher meaning. And they're also the meaning may depend on cultural associations. All sorts of things. So,
what kind of interesting or surprising, really, things that did you learn along the way with this project?
Probably the most surprising was that people were just sort of consume. They come to a website that in terms of news at least, they really go after one subject. And I think that makes sense. I don't know, you've seen sort of the development of like the media ecosystem generally, and they have like these one-track minds, and they keep delivering on certain subjects over a certain time period. So that was I don't know if it's surprising, but maybe like a bit disheartening. I was hoping that we want to get at sort of variety, and especially when we have like these long investigative pieces that journalists have worked on for a while, we want to sort of get at when is the best time to serve them. But I think that is, to do that, that's about personalization. And we do want to get more into personalization, but it is difficult given that, we're entirely cookie-based and we don't have registration.
It really, I think, speaks to a lot of what we see with the whole, filter bubble kind of situation. If you see such strong results by serving up more of the same, everyone is seeing the same kind of results, and that's why we're all getting more of the same, right?
Exactly. Yeah. But what can you do? I don't know. To talk to the editors about that one.
You mentioned inference stochasticity at some point in your talk. What was that referencing?
Yeah, that was. So I was trying to get this previously. It's really about when you make an inference on a new document vector. So it's initialized randomly, and if you do the inference multiple times, it's going to be a bit random each time. And that was a bit strange to me. you can look at the variance of the vector, the document vector, but it's always going to be a little different. We tried to get at this by just having a higher number of training iterations. And that was, I think, especially important because we were working with 100 length vectors for a number of reasons. I mean, I looked at longer vectors, but surprisingly, they didn't really perform too much better. So given that would have just taken up more memory, we went with the shorter one. And it was unusual. I mean, I was looking into why shorter vectors, there's a limit to how long they can be, and why shorter vectors tend to perform better. And no one really has gotten at that. And maybe something about overtraining, I don't know. But
that is surprising. That's 100 dimensions is commonly used for word vectors, and I would think that for a document you'd want kind of a richer space, and so you'd want a lot higher dimension.
Yeah, I agree, but it's not what we saw. So which was fine. And in terms of the stochasticity, there is another source of randomness in the context window. So we use GenSim for the document vectors, and the way the authors
And what is that?
It's a topic modeling library in Python.
Okay.
Yeah, which is really, really terrific. It's very fast. And so it handles LDA and word vectors and document vectors. But the way that they implemented it was when you're training, there's a context window that you can specify, but it doesn't always draw. Say if you say, okay, well, 5 words should be the window. It doesn't always draw 5 words. It draws randomly based on how. So the nearer words, the center of the window will be high. There's a higher likelihood that they'll be drawn. And this is how the original Word2Vec authors implemented the model. So that's what they did. So that is also, even if you weren't, even if you could see the document vector at inference, you would still have the source of randomness. So, I mean, another tactic would be to average the vectors. But, we did the sanity check where you're comparing the inferred vectors to the vectors at training. And in every case, they were, you came up as the result where, the nearest neighbor was themselves. So that was the check, and we figured we didn't have to do that. So
yeah, I still have some fuzziness around the inference thing. In this case, what's the input and what's the output of this inference step?
So the input is all the vectors that were trained previously. So it's not too complicated because these are really pretty simple models. Yeah, you're just keeping constant the words that were trained. So you're only looking up the words that are in a particular document that you're trying to infer. So those vectors already, and the output, the probability of co-occurrence for word-to-word pairings with those two weights established. Just through gradient descent, the vector that can change, which is the document vector that was newly initialized, that will change, that will sort of converge to the result that you found in training.
Okay, yeah, I don't know why I was kind of weighing out on that. So basically, you trained this set of document vectors based on some number of articles. I think it was 350,000 or something.
Yeah.
And then you've got some new article that was just some editor just hit publish or submit or whatever. You've got this new document. You're trying to figure out where it fits, and you need to produce a document vector for it, and that's the inference step.
Yeah, exactly. Yeah. Okay. But it's quite another worry was, because we're doing this in production. Another worry was just the speed at which you can infer. But it's quite fast. It was less than 10 milliseconds, and we do this asynchronously. So there isn't, if you're going to see a page, the inference has already been done. So we're just pulling that from a database essentially. And we're caching frequently, and we can cache at the feature level. So if a request is made for a particular article, and the request is, okay, we want a similar scroll. If it's not cached, we'll just pull it from the database, and it's very fast. But after the fact, that response is that string of articles is cached, so we can just serve it subsequently to users who come after that first one.
Meaning for a given article, you cache the preferred similar scroll articles.
Yes, exactly.
And do you cache kind of the exact order, or do you cache some number of similar ones and then randomize or something like that?
It's the exact response. There's a filtering step where we're only pulling from our. So the tech stack is, and this was sort of one of the more interesting parts in this whole development, is that we had to build out a data science platform, and it was great because it's just a Python web app and it's serving 1 million unique users a day.
Wow.
So to get actually, to come upon the realization that you can build a Python web app and scale in that way, that was great.
And is it kind of bespoke Python or something like Django or something?
We use a web app framework called Pyramid,
Okay.
which it's like Django, except there are significant differences. One of which is you can use something called SQL Alchemy, which is allows you to do database queries by writing Python. It's a ORM, and that's very powerful. So that was one of the main reasons for going with that. Other than that, we use Amazon AWS. We have a MySQL database that stores all of the articles, and then we use RDS or Redis cache for responses, and that also stores. So when we do personalize to some extent for like sponsored stories, and we serve up sponsored stories based on where user is in the world. So that's a user level feature. So we do that, and there's Redis is caching those responses as well. So we're able to scale with the users as well.
Okay, so you've got this Python-based web framework website, and it sounds like you're saying kind of starting this effort up, you didn't have a data science stack built up around this website, around the project. So what were some of the steps and thinking that went into building up that stack?
It sort of was built out feature by feature. The original feature was making recommendations for videos, because so I started at Reuters with one of their apps called Reuters TV.
Okay.
And we put the Reuters TV player on the website, and we wanted to. So there's algorithms that go into that. There's something called a program assembly algorithm that takes all the available videos that we can show and builds the best program based on the time that the user selects. And there's other sort of recommendations that go into that. So we needed to have a system to build that for the website and also for Reuters TV.
Meaning a user goes to the website and to some TV section, and they say how long they intend to watch.
Yeah, that's one of the key features of the app.
Okay.
And that was that was a really interesting data science problem as well, because it's actually so to determine, based on these 25 stories that have 3 lengths each of their variants, how do you, if a user wants to watch a program that's 10 minutes long, how do you take all of that content and get as close to 10 minutes as possible without going over? And how do you also make sure that you're filling the editorial requests of, well, we want to show X number of world stories and this many culture stories and that sort of thing.
Kind of like a weighted bin packing kind of thing.
Mm-hmm, yeah, it's called a knapsack problem.
Yeah.
And it sort of comes up in, like these coding interviews where you think like, I'm never going to have to use this.
Right.
But it was, I used it, and it was, and there were some sort of new, what I thought were new things that went into it. Like there's a multiple choice component where you're choosing, because each main story has 3 different variants. So that was very interesting. But yeah, the framework was really built out, feature by feature. So there's the scroll model.
Meaning, so you started with this video. We talking features at that level. There's the framework has this video optimization feature and a scroll optimization feature, or are you talking about lower level features that support the building of these different higher level features? I guess both. I mean, it's all contained there. So even the models are loaded into memory, which we're trying to actually get away from that and build out another framework where requests are just made to a machine learning app for, give us a scroll for this article. And the rest of the business logic that was built out during building this data science framework is still there. So yeah, there's that. There's I'm trying to think of other data science things that live on this web app. We do
something called a trending people module. So where we're doing name entity recognition on articles, and we're also looking at how articles are trending. And we have a little module on one of the sites on the website where we show people who are trending, and that's just based on the articles that they've been in and the fact that we've determined, okay, this person is being referenced, and also they're the subject of this lead of the article. So,
Okay.
yeah.
And are you doing that using that same document toolkit that you mentioned, or how are you doing the NER stuff?
Well, we have some in-house and some using Spacey, which is a sort of a general, really great NLP library. But Thomson Reuters, which is the larger company of Reuters, they built out a really terrific name entity system. So for any given article, they will tell you who's in it, and that's done in typical ways. But from that, there's also something that I built out was determining. We don't want to just pull out all the people in an article and show them like, okay, all these people are trending. The task is really, okay, well, we know these people are in the article, but who are the main subjects of it? And that is that's a task of dependency parsing and saying, okay, well, if you look at the lead of the article, this person is performing the action on this person. So let's take the subject and say that this person's trending. And that's sort of how we get at that.
And so you've got these different components that you use. You mentioned Spacey, and I forget the name of the other Gremlin.
Jensen.
Jensen.
Maybe
Okay.
Gensim. I'm not entirely sure.
Jensen.
Again,
Okay.
FFA.
Yeah.
I don't know.
You described this kind of data science platform. I'm trying to get at kind of what really characterizes this platform. Is it these higher level features that you're offering through the site, or are there lower level, components that you've pulled together that accelerate the ability to make the N+1 feature?
I think it's probably the features that characterize the web app.
Okay.
Just thinking in terms of the end users, that's sort of what they care about.
But who are they? Are they developers on the web app?
Oh, they're so I built the web app, but they're front end mostly developers. But yeah, if there's the sort of the tech that goes into the modeling, the lower level stuff. Yeah, I think down the line that could be something that we want to try to build out. And Reuters is we have a lot of resources, and even though the team is very small, that's something that I think that would be good to if you want to think about contributing to the community, data science community, that would be really terrific.
How big is the data science team there?
It's not big. It's less than 10 people. So we're trying to grow in different ways, but yeah. And then the developer team is also not big, but it's good to be small and agile in that way.
Cool. Anything else that you plan to cover in the presentation that we haven't already talked about?
I think we got to most of it. At the end, I do talk about just sort of the future of embeddings, and I think that there's some question now because they have been outperformed in some ways by different types of embeddings. It's a sort of a suite of models. One of the better known ones is something called ELMO, which is an acronym.
Called what?
ELMO, ELMO.
Okay.
It's a language model type of embeddings, and essentially it's getting at essentially just deeper context. So with normal word vectors, you capture the context of that word in a data set. But this actually gets at multiple contexts. So something called polysemy, which is the multiple meanings of individual words. So it's more advanced model. It's more complex, and there are also some sort of structural things about it that allow it to be used in downstream tasks, a variety of downstream tasks. And it seems that it's really outperforming in these tasks word embeddings, just sort of vanilla word embeddings. And I think a lot of the inspiration, this is just lifting this from this guy, Sebastian Reuter's an academic, and he developed Elmo, and he had a blog post talking about when is NLP going to have its ImageNet moment. referring to.
I remember that post.
Yeah, it's really thought-provoking, and getting at when is NLP really going to break out, and in terms of a single type of model or a single data set. That's why he was talking about ImageNet, and for computer vision, it was really both. Like the acceleration that happened so swiftly there was because of a data set,
right?
And then and also the models,
that
but
led to CNNs.
Yeah, and then doing transfer learning, moving those models and the weights that were trained on this very rich data set to other tasks. That was sort of the ImageNet moment. And with these embeddings, they're trying to get at universal embeddings that can be used in a variety of different tasks downstream. And they're similar to they're looking at context. They're sequence models. So you're predicting words based on context, but it's in a much deeper way, and it's bidirectional LSTMs. So given that they, it seems like the metrics are much higher for these. There's a lot of question about what's going to happen with the null word embeddings and document vectors. So, but we'll see.
Yeah, Sebastian and I are overdue to do an interview. We're supposed to be getting back in touch now, I think.
Fantastic. Well, he'll tell you much more than I know about them.
Anyone listening to this that was intrigued by the comment, we should be diving into that soon.
Cool. I'm looking forward to that.
Awesome. Well, thanks so much. It was great to have you on the show. I appreciate you stopping by, and looking forward to your talk.
Yeah, thanks, Sam. I appreciate it.
All right, everyone. That's our show for today. For more information on James or any of the topics covered in this show, visit twimlai.com/talk/183. For more information on the Strata Data podcast series, visit twimlai.com/StrataNY2018. As always, thanks so much for listening, and catch you next time.